the language of the universe.
But I don't understand it.
Hello everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 63, where today we are going to be talking about Newton's 3 laws of motion. The laws that basically changed science, like forever, in a big way. So here we are talking about the big ones.
I don't really know what they thought before the Newton's 3 laws. I guess it was more of just like you observe something and you write it down and you're like, okay, cool, this is a relationship that we have now. Mm-hmm. But I guess Newton was the first guy to really piece it together. And he was like, there's this thing called a force that we can feel, right? But, you know, before you have the equations for forces and things like that, how do you really describe a force? And how do you say like, oh, the same thing that like causes my hands to warm up when I rub them together is the same like thing that I feel when like turning in a car and my body goes the other way. Like they're both forces. It's all like transfers of energy and all that stuff. But when you put it all together in the 3 laws of classical mechanics,
basically,
you know,
yeah, he basically kind of invented the idea of classical mechanics. Like, I mean, classical mechanics is synonymous with Newtonian mechanics. So
I mean, it's based on
it is based on Newtonian mechanics. Right now, actually, technically, wait, that's not entirely true, because in today's day, like, we also have these things called Lagrangian and Hamiltonian mechanics, which also constitute classical mechanics. So technically,
but it
Newton
started off, right?
Yeah, exactly. But Newton started it off. Like, he was the first one to start this whole it's amazing because some of his laws, obviously, like, now we think about it as, you know, it's obvious. And I'm just going to give the 3rd law as an example because it's so straightforward. Every action causes an equal and opposite reaction. You know, like, you push the wall is pushing you with the same amount of force. Like, that idea is it's so intuitive that anyone can think about it. But the fact that he did, and he put it into these papers, put it into these mathematical relationships, beautiful. And we're just going to dive into those today.
And also, I wanted to say, actually, I guess we'll just save it for later. Also, I kind of forgot. But let's just go into the news, and then I'm sure I'll remember later.
Let's go into the news.
We are close to 9,000 followers now on Spotify. I'm sure this time next week we will be at 9,000. So make sure to hit that follow button if you're listening to us on Spotify, Apple, or anywhere. Actually, it doesn't matter. Even YouTube. Hello, everybody on YouTube.
Just hit it.
Hit the subscribe button.
Hit that subscribe, hit that like button, help the YouTube algorithm. Because especially nowadays, you know, I've been seeing like some of these videos, you know, I mean, you guys have definitely seen it, you know, from like 7 and 8 years ago, just popping up into existence. Like, this algorithm is crazy. So we need to take advantage of it. And we know all the listeners here at the Math and Physics Podcast, you know, they love physics, love math. They hopefully love algorithms. So, you know, help out the algorithm. Go click that like button.
Also, almost at 130,000 downloads in total.
That's nice.
It's gonna be a good day when we reach 1 million downloads. That's gonna be awesome.
That's a little farther from.
I don't think it's that far, to be honest. I feel like by the end, like very easily, by the end of this next, like, our 2nd year of podcasting, we will be at 1 million. Like, if we can go from 0 to 130,000 within a year, then going from 130,000 to 1 million shouldn't be that much harder. You know what I mean? Anyways.
I can see that. I mean, especially, you know, like, we're creating content like every week. You guys know we have this stuff out. So, like, I think I can,
for sure.
Anyways, we gotta wait and see. The
point is, if you are listening to my voice right now, pause the podcast. Go tell a friend to go listen to the podcast and then come back.
I love it.
So comment of the week. Today we have a nice comment, simple, very to the point, by Will Ring. He says, great podcast, comma, 10 out of 10. Thank you very much, Will. We
that
appreciate
10
the
out of 10.
comments. If you want to be the comment of the week next week, make sure to leave a comment in the YouTube comment section under this video, and you might get selected as the comment of the week next week.
Yep.
Other than that, you can find us on Instagram at math.physics.podcast.
We're almost at 1,000 Instagram followers, by the way, so that's kind of nice.
Yeah.
So,
That's
you
true.
know, if you guys are on Instagram at all, you know, go on Instagram, follow us. Because also, if anything, like our first place to update people is Instagram. Like we'll either make a story, a post, or something about it, and that's our first place because that's just logically where we can reach out to our followers the easiest and fastest. So, you know, if you have an Instagram account, go follow us at math.physics.podcast.
100%.
Yes, sir.
All right. Let's get into
it.
Newton's 3 laws. Obviously, should we just troll the audience and start with the second law?
The second law is the big law, in my opinion.
Nah, I was kidding.
That's the biggest law, but so I do not think we should start with that.
I was kidding. We're obviously
were.
going to go in
Chronological
numerical
order?
order.
Did he actually wait? Do you think?
No,
I never
I
thought
don't think
about
it's
this.
chronological.
Yeah, I never thought about the whole reason behind 1, 2, and 3 though. Like,
I think it's just like he's like, okay.
like why is it one?
He had
like,
to.
Why isn't it
He
the
had
other
to
way
give
around?
a number. He had to
just-
give numbers to them. So he's just like, I have 3 laws.
Just 3 laws,
This is
just
1,
so it's
2, 3.
basically
There
just
you
a
go.
random number given to it. It's not like a significant. Okay.
I mean, I don't know that. For
I mean, we
sure.
don't know.
Like, I
We don't
could
know
totally
here.
be
We're just
wrong,
thinking. We're just thinking. Yeah, we're just thinking out loud. But like, it could be. It could be something deeper.
I guess.
Who
So
knows?
here we go. First
Yeah.
law, as stated, a body moves with constant velocity unless acted on by a force. Okay, so now let's deconstruct this sentence. Okay, this basically says that, and obviously, when we're talking about forces and things like that, it's important to kind of detach ourselves from this earthly view, if you know what I mean. Because in our heads, like, if we roll a ball on the ground, and it'll just like eventually, you know, it'll just slow down and stop. But that's because we don't like obviously register like the forces of friction and all that stuff. But now imagine you throw a ball in space. Now it's easy to imagine, like, obviously it'll move at the constant velocity it was released at, and, you know, until maybe it comes close to a planet or someone hits it, until some force acts on that ball, it will remain at a constant velocity in a single direction. Yes, go ahead.
A nice way to think about it, though, like another nice way to say it, listen to this. And this is, I don't like believe this. I learned this in grade 7 or 8 physics in India, and I literally still remember the exact definition. Hear this out, yeah?
I don't even think physics was a class in Canada, grade 7.
In grade 10. Yeah, exactly, right? A body at rest will remain at rest unless a force is acted on it. Part 2. A body in motion will remain in motion unless a force is acted on it to resist its motion. So basically, a nicer way to, instead of using the word velocity, because you use the word velocity, you know, like constant velocity, and then you're like, you know, I don't know, there's just another factor to think about. But like the main idea behind the first law is that, hey, if a box, like, again, think about space mainly, because like on Earth, there are a lot of factors that we don't think about, like gravity, friction, like just things that we don't really see, that we don't really register, as you very well said. So like if you think about space, and you just place like absolutely nothing, isolated space, you place like a ball there in the middle, it's going to remain at rest forever. That's the idea. And if, let's say, you just move it, just touch it in a little direction, it will continue in that direction at that same velocity, or speed, I should say, same thing, but forever, basically, until a force is exerted on it. So like that might be a nicer way to put it, but like it's basically essentially the idea.
The key word here is, in fact, velocity.
Okay.
Because, I don't know if we talked about vectors before. I'm sure we have.
I think we have, yeah.
Velocity is a vector.
It is.
Which means that there is a magnitude and a direction. And notice that I said a body moves with constant velocity. This means, okay, what can change a velocity? Well, a velocity can change in magnitude and it can also change in direction. So here are maybe some examples that maybe some people haven't thought about before. The obvious one is, you have a ball moving with some velocity and then someone hits it and then suddenly it's going faster. So that means a force was applied onto the ball and now the velocity vector of that ball has changed. It is now longer, it's going faster, whatever. But just because a velocity vector doesn't change in magnitude doesn't mean a force is not applied. For example, if you have a ball on a string,
Very smart.
and you're spinning that ball around, notice that the ball is going at the same velocity all the way around the revolution, but
Speed.
or sorry, yeah,
same
you're right.
speed. Yeah, you just
right.
misspoke. Yeah,
You're right. Same speed.
Yeah.
But the velocity vector is constantly changing direction. And that's because at any point along the trajectory, the velocity vector is perpendicular to the tension vector on the string. And so it's constantly, it's hard to explain with my hands, you know what I mean?
Yeah, especially for the listeners. Yeah.
Yeah, but as the velocity vector goes around the circle, the tension vector follows it. It essentially just traces
It's
it
basically
all the way
like
around.
a right angled,
Yeah.
thing, just like
That's
tracing the circle, the center of mass of the circle or of the ball throughout the entire circle.
And
Right,
so
like,
that's
the idea.
that's the centripetal force, which doesn't change the speed of the ball, only changes the direction, but it's still a force.
Yeah, but we didn't really get into why it's a force, right? Like you were talking about the fact that it changes velocity. And now like a nice way to think about it is, well, okay, now we know the magnitude might be the same, but we know for a fact that the direction changes. So we know the velocity is not constant. Now, if the velocity of an object is not constant, it's accelerating. Now, for any object that's accelerating, there is a net force that is not equal to zero that is being applied on that object. So, got from the fact that the speed is the same, to the fact that the velocity vectors are different, to the fact that it's accelerating, we can now conclude that there must be some force that is acting on this ball or on this object, whatever that we're swinging, to remain in its same trajectory. And it turns out in the string situation, it's the force of tension that what we call the centripetal force, right? Like that centripetal force is basically the force that points from any object towards the center of the
point of
the
rotation.
trajectory of the trajectory, right? Like the center of the center of the circle points there, and that's basically the idea. Sure. We went to centripetal force without really kind of like skipped a little.
I mean, there are 4 forces that we see on an everyday basis.
Yeah.
And this is the gravitational force. This is the force of friction. Tension is the other one. And wait,
Normal?
I might have been mistaken. Yeah, the normal force. Yeah, you're right.
Normal
Yeah,
force.
so those are the 4 forces. And actually something that I know is kind of like when I was learning about the normal force, I didn't really understand it, right? I was like, if you're on an angled plane, the normal force is perpendicular to that plane, but then when you're flat, it's always okay. The point is the normal force is always perpendicular to the surface. And this is the reason why when you're standing on the ground, you're not accelerating with respect to your the frame of the earth.
Yeah,
right?
Technically you are in from general relativity.
But what was I gonna say? Oh yeah, the gravitational force on your center of mass, I guess, is completely offset by the 2 normal forces on your feet. Mm-hmm. You know what I mean? Mm-hmm. Also, yeah, I was gonna compare this to inclined planes, because as soon as you look at an inclined plane problem, which is very common in high school physics and all that stuff, the normal force remains, of course, perpendicular to the surface. But now, this is why we see an acceleration of the box, is because all of a sudden, the entire, like the gravitational force always points down, but now it's offset by the normal force, which is now pointing at a different angle. And so you do get an acceleration in the direction parallel to the inclined plane.
And that's also where we get like work and stuff like that from. Oh, we can maybe touch into that later though. I mean, I was just thinking about inclined plane and you brought it up, so I was thinking about it. But anyway, so that is a very, understanding forces is a very important consequence of the first law, even though that is more emphasized in the second law. Like we actually kind of spoke a lot about the second law of motion while describing the first law. But one thing I do want to talk about in the first law is inertia. So inertia is the amount of resistance the body poses to motion. That's a nice way to think about it. So
Actually, change in motion.
Change in
Because,
motion. You're correct.
yeah, 'cause
Change in motion.
There's
You're
no resistance to just motion.
Absolutely,
itself.
You're correct. So what that means is a heavier box is harder to move than a lighter box. It's the easiest way to think about it, right? So a heavier box inherently has more inertia than a lighter box, and therefore, if a heavier box was, let's say, coming at you like a huge box was like coming at you, you'd probably get trampled by it. But if a small one was coming at you, you can probably stop it. So
it depends how fast it's going.
Depends. Okay, yes, you're right. You're very right. Speed is also a very important component. It's actually mass and velocity that becomes a very important component in measuring how hard or the resistance to the change in motion. Basically, if
we're also going to talk about we're going to talk about momentum very shortly.
Exactly.
But yeah.
Exactly. So that's basically a way to measure it. But I did want to just touch on inertia because it's an interesting concept. So like the idea behind inertia is like there's an inertia of rest and inertia of motion. So inertia of rest is basically an object is at rest. So how much force or what would you need to do to change its motion? So to make it start moving. And inertia of motion is when an object is already in motion and you need to stop it. How much force would you need to apply to stop it? So they're just two different ways to think about. And again, all of this derives from, the original first law of motion, where all can be applied.
Technically, those are both the same thing.
Yeah.
Because
they are. It's the same thing. I'm just describing it in two different ways, right? Like when a body's at rest and in motion.
But imagine this. Yeah. In one frame, you're in your frame of reference, the box is moving. And so you say, oh, the box has an inertia of motion or whatever you called it, and I need to stop that box. But then in the frame of the box, you're the one that's coming towards the box and you're putting it in motion. Yeah. And so little touch on inertial frames there.
I was also gonna say, that's also a big thing to make the similarity. So the reason the inertia of rest and inertia of motion are the same thing is because speaking from a relativistic perspective, like frames of reference, being in motion at constant velocity and being at rest are the same thing.
It's the same. Yeah.
It's the exact same thing. And that's one of the consequences of, understanding inertial frames. So that's why for a frame to be inertial, it must be traveling at constant velocity. It cannot be accelerating.
Yeah.
So that's also something we can... Yeah.
The thought experiment that I always love to talk about is, imagine a universe that is just completely empty, and then you have two people. All of a sudden, you see, they're both going at a constant velocity, and they cross each other, right? And so from the perspective of guy number one, there's someone out in deep space that is coming towards them and then passes them and then keeps going the other way. Yeah. From the perspective of guy number two, the exact same thing happens, except from the other way. But now from God's perspective, right, from a third person view, you just see two people coming towards each other and crossing each other. So it's kind of like, which frame is the right frame? There is no right frame, right?
There's no right frame. Exactly.
You could be tracking... You could be tracking any point in the universe at a constant velocity, and the physics will always work out, no matter what. And that's why it's so beautiful. Because
the physics, the exact same physics can be applied to an object at rest than to an object in motion. Like the ideas behind, looking at them at rest and looking at them at motion is basically the same thing. And that's a very fundamental concept, because that basically relates to how, like, what we perceive as force, right? Because when you say the net force on an object is 0, that could mean two things, right? That can mean it's at rest or it's in constant motion. And the fact that that's what that means is what kind of points us in the direction to the fact that they're the same thing. Because the net force is 0 in both of these situations, they must be very similar situations. And that's kind of like one thing that we can conclude from the first law. We can also talk about moment of inertia, though, if we want to get into that.
Now I want to talk about inertial terms.
Oh, yeah, you were talking about this.
Equations.
Let's get into that before. Yeah.
Okay, yeah. So in equations of motion, there is usually, I've only taken first year mechanics. I'm taking second and third year mechanics next year. So, I might find some interesting stuff in there. But from what I know, in the equations of motion, there's always an inertial term, as Ray, you said, like a term that opposes motion. And when we're talking about translational motion, for example, the mass of an object is the inertial term. When you're applying a force in one direction, the thing that makes it so that you have to apply a force is that mass that you're trying to change the velocity of. Okay? But because I really enjoyed learning about this when we were in first year, when we were learning about rotational motion, we started off by deriving the analogous equations, like, just position, velocity, acceleration, but all, in terms of rotation. And then, of course, there's the analog to the force equation in the rotational world is the torque equation. And the inertial term in the torque equation is the moment of inertia, which is different from just mass. Essentially, it's an integral. Like it is an integral.
I mean, it is. It's the rotational variant of mass. It's a way to think about mass in rotational terms, right? Because
but
as you were,
No, I was gonna say technically it's an infinite. It's like a sum of, if you're like, how we derive it. We talk about one point, and if you have one point that's rotating around the point of rotation, I guess, then the equation is mass times distance squared, right? And if you have multiple points that are all rotating around the same center of rotation, then what you do is you just add all of those individual masses multiplied by each distance squared to that center. And then, of course, the natural extension to that is like a continuous body. So if you have, like, for example, just a sphere that's rotating around its own axis, then you have to start integrating over.
It might also be different densities. It might, your problem could get a lot more complicated.
Pretty complicated.
Yeah, but the idea is still there, and the moment of inertia term that you were talking about, the moment term, is a very important concept because it's so analogous. It is basically analogous to mass in translational terms, right? Like the way you were saying, like if an object is at rest, how hard it would be to push it would be dependent on its mass. And the same way to think about it in terms of rotating things, it's dependent on its moment. Now, the moment, as you very well said, is just, the sum of all of these individual mass and distances. And the interesting thing about it is that there can be some crazy shapes. Like we've seen some really crazy shapes where, there can also be different distributions of mass. Like, let's say, for example, on like a vinyl record tape, you're trying to find, I don't know why you would, but you're trying to find some equation. You would be talking about the distribution of the mass of how heavy each and every, section is. So there would be a lot of different takes to something like that, like a more complicated situation, like a more complicated system. But it all revolves around the moment of inertia, which is basically, again, the amount that the body The amount that the body resists a change in motion. Okay.
Wow, that was
I
great.
could not say that word for the
That was
love
great.
of it. Okay, resists. That's the word. Yeah.
Yeah. So, if you don't believe me, listen to
Okay.
this little example, okay? In terms of, y is like mass times distance squared and then like summed over the entire shape or whatever. Why does that represent the
Okay,
inertial
let's hear it.
term? Okay? So now just think about this. I'm not going to literally go through the derivation, but here we go. You have a box. You try to accelerate it, whatever. It takes this amount of force. And now the box grows in mass. It's harder to accelerate that box, right?
Mm-hmm.
I.e., the mass is the inertial term. Now, let's say you are like spinning around. You have a mass on like a string, and you're rotating that mass around, okay? But now it's different. Oh, wait, hold on. My mic is only recording halfway. Okay,
Oh.
we're good. Okay. So now you're rotating mass on a string. There are two situations that can happen. One, if you increase the mass of that object that you're rotating, it's going to be harder to keep spinning it, right?
Mm-hmm.
Now, case number two, the mass stays constant, but the distance from your hand, the string, gets longer. It will also become harder to rotate that object.
Mm-hmm.
A very easy example is when you see like dancers, when they do like a spin with their arms out, they rotate slowly, and then when they bring their arms in, they start rotating super quickly.
Mm-hmm.
That has to do with the moment of inertia, because your mass distribution in general gets closer to the axis of rotation, and so it's easier for your body to rotate, so you start spinning faster.
Mm-hmm. As you said, it was dependent on M and R, right? Like in a relationship, like MR squared, but like that's the relationship basically between moment of inertia and these things are mass and radius, as you very well said. So yeah, so it's dependent on how you increase these things, and also it's the square of the radius, which is also interesting. So if you double the mass, it will be X amount of force, but if you double the radius, it will be quadruple the amount of force. So that's a nice way to think about it, because of the relationship that they have, right? So yeah, so that's basically the moment of inertia, and like kind of understanding the differences between like, rotational and translational just a little bit here. Kind of touched on torque too. But I think now we can move on to,
I think
do you want to talk anything more on the first law?
No, I was just gonna say that in the near future, maybe
Okay.
we're gonna make an episode on rotational motion, but I think we might have to
Let's do it.
we might have to whip up some ideas to talk like an entire hour about it.
Yeah.
But it is an interesting
Rotational
topic.
motion is really interesting because we can get, angular velocity, we can get angular momentum, we can talk about that kind of stuff, all of that good stuff. I mean, I said the word momentum, and now we naturally need to move into it. But yeah, so there are a lot of cool things that we can talk in the rotational episode for sure. But now let's focus on Newton. Let's focus on Newton's second law. The second law of motion is, the popular F equals ma equation that everyone knows and loves. But basically, again, the purpose of that equation, kind of resorting back to what I was talking about when we were talking about the first law, the main purpose of this is simply to relate the fact that acceleration and force are related, right? Like, I think that's the big thing. Like, with E equals mc squared, the big thing is that energy and mass are related. Like with F equals ma, the big thing isn't the equation. Like, okay, cool. Like you found out a relationship. But the big thing is that force, or net force, I should say. I should keep saying net force, and acceleration are related to each other.
I mean, I think the mass part is equally as important.
No, it's important, but the idea is that without acceleration, there will be no force. And with acceleration, there will be a force. So mass doesn't really have a play in that, is what I'm trying to say. It's because of the acceleration that we register a force. You know what I mean?
Sure.
Yeah, and we can talk. So in the previous episode, in episode 62, if you guys checked it out, with Dr. Pekka Sinervo, he spoke about something quite interesting, a very interesting idea that Newton actually originally thought of as well. Like, this was his original interpretation of force and acceleration. That force wasn't really an actual measurable quantity. It was simply a theoretical concept. What was measurable is the acceleration. We look at a body, we watch it accelerate, and we say there's a force. Even if someone like hits us like a force, what we're really feeling is our body moving. And via that motion, basically that acceleration, we are interpreting that there was a force applied. So that is a big thing that, the second law gets out. Just that relationship between both of these variables.
Mm-hmm. And also, a lot of people refer to the second law as F equals ma, but there's actually another way to look at this law. And
Let's see it.
You do need like a little bit of calculus notation here, but I'll try to be very explicative. So the velocity is the rate of change of the position with respect to time. So we're going to say it's dx by dt, right? That's just notation, okay?
Yep.
And then acceleration is the rate of change of velocity with respect to time. So it's dv by dt, but also since v is dx dt, then we could say it's the second derivative of position with respect to time. Now, momentum is defined, it's just a quantity defined by the mass times the velocity. And so as we talked about a little bit earlier, if there's a big box, very heavy, moving towards you at a slow velocity, right, it's going to be hard to stop that box. But it will be equally as hard to stop a light box moving at a fast velocity, because the momentum is proportional to the mass and velocity. So if you tone down the mass, increase the velocity, you can have the same amount of momentum coming at you from two different types of boxes, right? So the force is actually defined as the rate of change of the momentum with respect to time. And this actually relates to the rocket science episode that we did, because notice how the rate of change of momentum is the rate of change of mass times velocity. And so not only can this, like, if your mass is constant and you know that for sure, then that just becomes mass times acceleration, because you can pull that out of the derivative.
Well, not
But
acceleration, just change in v. Oh, because you're saying force equals force. Yeah.
So yeah, force is going to be mass times acceleration.
Yeah.
But like we talked about in the rocket science episode, if you have an object that has a variable mass and a variable velocity, then it's not so simple, because now all of a sudden, for my calculus students out there, you have a product rule because now your mass is a function of, it may be time or position, and your velocity is also a function of time or position. And so you have to do some product rule, chain rule business, and your equation for force is going to be very more complicated, whatever the
More
word.
complicated for sure.
Yeah.
It's going to include all of these important terms, but the idea behind that again is that momentum term, right? Like understanding that change in momentum relationship with force. So now we can not only understand the relationship between acceleration and force, but now we also have another relationship to go by, the force and the change in momentum, which is an interesting thing. Have we spoken about momentum? I don't think we really touched on it too much. But like, again, I mean, we were kind of discussing it this whole time, basically like your mass times velocity. And again, that's more translational momentum. And we can also kind of
and one awesome thing about momentum is the conservation of momentum.
That's a big one.
But I guess we could save this for another episode where we talk about energy and momentum together. That would be good. Anyways, we can talk.
I think conservation of momentum is quite important in this kind of regard, and it wouldn't take too long, because it's just saying that I think it's an important concept because momentum, like energy, is an important concept by itself, and we can make an episode on that. But I don't think we should sacrifice what we can talk about here.
Well, go right ahead.
You know what I mean? You know what I mean? So momentum, as we were talking about, very, very important concept, you know, relating, as you were saying, like, you know, the amount, like how hard is it to stop an object or to move an object. It's dependent both on its mass and velocity. So here, the conservation of momentum law is kind of a universal law, which is basically for any isolated system, no matter what happens, no matter what interactions are occurring, the total momentum of that system will always be the same, no matter what. And what does this entail? Well, think about a very simple example, and this is usually what people start with, a billiard ball, you know, playing pool, for example. Like when you hit a ball and it hits another one, I mean, in a perfect world, obviously we don't live in a perfect world. Like there's still like, you know, edges on the ball and stuff like that. But in a perfect world, that ball would transfer all of its momentum to the other one, or the ball would hit the other one and they would both take some portion of the momentum. Or, you know, the ball would just rebound and take all the momentum. Basically saying that the momentum of those two balls, the total momentum of those two balls, will always be the same. So in an isolated system. Kind of the gist of the conservation of momentum. Very important idea. Also, I believe, thought of from Newton's laws of motion. Right.
Probably. I mean,
Probably.
I think like conservation of momentum is like you can derive it directly from the third law, which
yes you can.
Can we?
So probably.
Are we done with the second law? Yeah. Okay.
Yeah, we can get into it. Why not?
So the third law states that for every force on one body, there is an equal and opposite force on another body. Okay. As Brehan said, if you punch a wall, the reason why your hand will hurt is because the wall exerted a force that was equal but opposite, right? It's the same reason why you can't just, you know, push a tree over. It's because the tree resists the force that you put on it.
Well, not always equal and opposite. Like if you just break the wall, then it's not going to be equal.
Well, that's because then the wall has an acceleration.
Exactly. So it can't provide enough normal force to counteract your punch, so it would break it, right? Exactly.
For sure. But something that's interesting, right, is that when you jump, if you just go outside, you don't even have to go outside, you can just jump. The force that you apply on the earth to accelerate your body upwards is the same force that the earth applies on your feet for you to be able to jump. And so the earth and your body are both moving away from the common center of mass with the same like transfer of energy. If that does that make sense? Like
same trans.
Like for example, you're changing your momentum from 0 in your frame to whatever your mass is times the velocity you leave the earth at, right? But you're giving the earth the same amount of momentum, but in the opposite direction.
Momentum is a vector. It's a directional quantity. So if you are getting momentum upwards, it's the reason it's still conserved is because the earth is getting momentum downwards, right? So it'll always cancel out.
You are actually single-handedly moving the entire earth downwards by jumping. So
that's a way to think about it.
That's fun.
There was a really cool video I remember called "What if everyone jumped at once?" Like, what if everyone on the earth jumped at once? The thing is, it would be a little interesting. You know why? Because the land is not symmetrical around the earth. Like, you know, it's not equal in like the first quadrant as it is in the third, and the second as it is in the fourth. So if people jump, I don't know, you know,
I don't think anything would happen to be
No, there's no way, because obviously we cannot push out that much force, because us jumping up is literally nothing for the earth. Literally nothing. So it wouldn't really matter. But yeah, so again, another important consequence of this is understanding the normal force that you were talking about, right? Like just thinking about, okay, maybe we can talk about that later, but like thinking about just a book on a table, like why is it remaining on that table and not falling to the ground? Because the table is applying a force that is equal to the book's force of gravity. Now, the interesting thing about the normal force is that it keeps changing. It keeps changing dependent on how much weight or mass, or technically weight is the correct word, how much weight is being applied on it. So the heavier the object, the more the normal force the table or whatever will provide. Now, obviously, there's a breaking point, which is when, as we were saying, like the normal force cannot equal the gravitational force, and it simply breaks, hence accelerating the table.
But this is just a strictly like structural property of the table that you're
there's also a consequence of simply the normal force, right? Like understanding the normal force, it is obviously it is a force, but it's only a force present to counteract another force. That's the only reason it's there. The only reason it's there is to counteract something else. So it's not really its own force. One thing we didn't, and now that I'm saying not its own force, I'm really thinking of the centrifugal force that we didn't really touch on when we were talking about first law.
I mean, isn't centrifugal? Yeah, it's an invisible force.
Yeah, the centrifugal force is literally an apparent force that is acting.
Felt, but it's not real, right?
No, it's not real. It's the.
No, but that's what I said. I said it can be felt, but it's not an actual force.
Exactly.
So, for example,
what's the way to think about it?
Wait, let me say this.
Yeah, go for it.
If you're in a car and you are turning, a 90 degree, you're turning to the right. Beautiful. Okay. So what happens is that the centripetal force is actually the friction between the tires and the road, right? Because that's keeping the car in its orbit around the
in its circular track,
right?
In its circular track, exactly. Yeah.
So the sorry, my mic is just
glitching
recording halfway.
Not to worry.
Hello. I don't know why this happens.
Oh.
Okay, it's back.
Yeah, much better.
Okay, so what was I gonna say? Oh yeah. So the centripetal force is between the tires and the road. It's the friction, right? And notice how if the road is icy, for example, there's not enough centripetal force to keep it in its orbit. It'll go off, it'll go straight, for example. That's because the car requires a force for it to go around in a circle, for it to change its velocity vector, the direction in this case. But if you no longer have that friction, then you no longer have that rotation and your car just goes off in one direction. Mm-hmm. But let's say it's a nice summer day. You're in that car. Let's say you're not wearing a seatbelt. What happens is that your body is moving straight until you get to the intersection. And then once the car starts rotating, or starts moving around the corner, your body is still moving in that straight direction. So, in your frame of reference, you're actually going to be moving. Let's say you're doing like a right-hand turn. Your body's going to be moving to the left. And this is called the centrifugal force, because you feel a force when you turn to the right. You feel a force acting to the left, right? In the opposite direction of the centripetal force.
That's more inertia, though, because the thing with that that's a lot more inertia, because the idea behind a car, like sitting in a car, is that the moment the car turns, your butt, like that's sitting on the seat, is moving to the right, but your head is still moving straight. So that is why your whole torso, including your legs, moves towards the right, but your head moves towards the left. It's not actually moving towards the left. It's actually moving straight in the head's frame of reference. But isn't that the centrifugal
force that you feel? Like it's not an actual force, but it's just the force that you feel that's pulling you to the other side.
I guess that is No, that's right. Yeah. That is yeah, okay. That is actually a way. Yeah, that's a valid way to think about the centrifugal
unless I
force.
just totally don't understand the
No, because
centrifugal
the
force.
way I love to think about it is like in those kiddie things. You know, like when what are those things called? Like, you know, when you run
No,
around it
okay.
and then you go in those
Yeah, yeah.
circles.
In that case, right? In that, if that's your example for centrifugal force, then what I said is completely valid.
No, I mean, no, that's what I'm saying, right? No, that's what I'm saying. I think yours still works, but it is a little bit more inertia because of the car situation, because of the fact that you're sitting in a car and
It's the
your
exact
body is
same
moving
thing,
in
though.
one direction.
It's no, Ray. It's the exact same thing. Because imagine the car's on a circular track, then your body's just gonna be a bit on the door the entire time, and that's exactly what you're describing. Is the carnival things that spin around. You know, isn't that what like you're trying to say?
Yeah, basically, yeah, okay, yeah. Very similar arguments, both centrifugal forces. I know some people say, I used to say centrifugal, but then a lot of people say centrifugal. Doesn't really matter. Idea though is that it's called an apparent force, right? Basically,
Okay,
as you
right.
very well said, it's not a real force.
Right. So on Wikipedia it says the centrifugal force is an inertial force. So it is
Okay,
in
well,
fact
okay, so then
what we're saying.
okay, perfect. So we're saying the same thing then. So that centrifugal force is basically the effect, the feeling of inertia is a way to think about it. Because again, that car example is a very nice example, similar to like why people say you should wear a seatbelt, right? Because if you're like sitting in the middle and someone were to immediately brake, your legs and your entire torso is still sitting on the car, like it's still connected to the car, or at least trying to, but your head is not. Your entire body is not. So wait, when I say torso, I meant top. I meant bottom, by the way. Sorry, I did not mean torso. I was not talking about the torso. I meant the bottom part of the bottom part of our body.
Yeah.
Sorry. So, anyways, you guys know what I mean, though. Like, there's one part that's isolated from the car that's free to move, and when that thing moves, the whole body moves with it, right? Because of inertia, and that's another way to think about it, right? Like that's where inertia kind of plays a very important role in all of these laws, almost, right? Like inertia is very important. It comes in the first law as just what it is. It comes in the second law as momentum. And here it is.
I could just imagine like you giving a lecture. You're like, you walk into the class, you're like, all right, students, welcome to your class on Newton's laws. Now imagine you're in a car crash.
I can see that. I can see that. I can see
the reason why you fly through the windshield is
Oh, I can see that.
I mean, it's a good example for.
It is a good example. It's a nice way to think about it, right?
Maybe, it's just funny, but
yeah.
But yeah. So we're talking about the third law. Which, you know, I was talking about the Earth and jumping off of the Earth, which actually reminded me of the Newton's law of gravitation. Okay.
Oh, the big one. Or not? Well.
It just says that, I mean, it gives you a formula to calculate the gravitational force, you know, of an object that's orbiting. But one thing that I do remember from first year is that our professor, he was talking about like how Newton really thought about these ideas of orbiting and all that stuff, and he said, well, this, I don't know if this is true, but he said that, you know, Newton went on a tower. He was standing on a tower and he threw a rock down. And he's like, okay, there's an arc to that rock. And if I throw it faster, I throw it harder, that arc is broader and the object goes further. Now, what if I just keep throwing it harder and harder, and that arc extends beyond the horizon from where I can see? How hard do I have to throw that rock for that, like the trajectory of that rock to go beyond the horizon and hit me in the back of the head, right? And that's kind of where he started. Like, he went from his equations that described projectile motion and all that stuff and transferred to orbital mechanics, which is at the end of the day where like Newton's gravitational or universal gravitational constant came from, and where the law of gravitation came from, which essentially states that the gravitational force on a satellite, for example, is proportional to the mass of the satellite, the mass of the Earth, and also the distance between the two centers of masses squared. So there you go.
Well, that's the formula. Not that many listeners are really going to do much with that formula, but that's the idea.
No, but that's just
again, the relationship is important, right? Again, like in this, it's really hard when we're trying to explain like science, like a lot of scientific things that are very well explained in a formula. But again, the main purpose of the formula is simply understanding the relationship. So what you were just saying right there is basically a nice way to say, hey, the force of gravity is directly proportional to the masses of both the objects. So if you increase them, the force of gravity increases, and is inversely proportional to the square of the distance between them. So you increase the distance, the force of gravity, like you double the distance, the force of gravity will 1/4, right? Basically, because it's proportional to 1/r squared. And a very interesting consequence of mixing the universal law of gravity with Newton's third law is that the force of gravity that the bigger planet, like for example, let's take like a big planet and a satellite, like a moon. When I say satellite, I mean like a natural satellite, like a moon, like an orbiting moon or something. So so the force of gravity that is applied on the moon towards the Earth is the same that the moon applies on the Earth towards itself, towards the moon. Now, the interesting thing about this is where we get to, I don't know why, I just thought of this and I'm like, it's just a cool thing to talk about. Tidal locking.
We already talked about this.
Oh, did we already spoke about it?
Astronomy, yeah.
Oh, I think we did, right? I mean, let me just touch on it for those that might have forgotten. Yeah. Tidal locking is a really interesting phenomenon that you see in various planetary systems with a planet and its satellite, again, natural satellite, where basically because the planet is more massive, obviously, than its satellite, it is tugging, or the force of gravity that it is applying on the satellite, even though the magnitudes are the same, relative to the size, relative to both the masses, it's kind of more on the smaller satellite. You know what I mean? Like pushing the Earth with 1 Newton is going to be harder than pushing the moon with 1 Newton, even though 1 Newton is nothing. Just that analogy is what I'm trying to get through. Like, because it's a smaller object, it's easier to push around. So because the satellite is naturally a smaller object than the planet it's orbiting, it gets pulled technically a little bit more than it pulls the planet, even though they're pulling the same. It's just the effect on that planet.
This is just easily explainable by what we were saying earlier, how the inertial term here is the mass, and so it's the Earth opposes that pull from the moon more than the moon opposes the pull from the Earth, because the moon has a smaller inertial term, even though Newton's third law, they both feel an equal force pulling towards each other. It's just the moon, it appears, I mean, from our perspective, it doesn't even look like anything's changing except for the tides, which were only connected to the effects of the moon relatively not that long ago.
So that's definitely, the inertial term is a better way to put it, to think about what I was saying. I know I was kind of fumbling in the end, but that understanding that will then lead to the fact that, hey, because this smaller object is feeling a greater force, even though you guys now know that's not true, but feeling a greater force, not actually greater force. So now that the smaller guy is feeling that greater force, what's happening is there's one side of that planet that continuously gets tugged towards the bigger guy, right? Because as it's orbiting, there's going to be one side, let's say the satellite's also rotating in its own axis, there's going to be one side of that satellite that continuously gets pulled towards the planet. And basically what this causes is a slight bulge in the satellite. Also, because remember the forces are the same, it also causes a slight bulge in the planet, So in the mother planet, it also causes a slight bulge. So for example, a commonly known fact is the Earth is actually not spherical, right? It's a lot. It's I think like some 40 or 50 kilometers wider at the equator than at the poles, right? Because it's got slightly a bulge. But now the moon, having such less mass than the Earth, is affected a lot more. So the bulge is so prominent that it basically faces the Earth forever and basically cannot rotate anymore because that one side is so much closer to the mother planet. And that's the idea behind tidal locking because of the fact, because of the mixture between the universal law of gravitation and the fact that these forces are equal. Because these forces are equal, this is possible. Right.
It doesn't face the Earth because one side, I mean, if you go deep into it, I guess it is because one side is being pulled more than the other. Yeah. But it's actually because the Earth is rotating, right? The bulge from the Earth is actually it causes a torque because when the moon was rotating, the torque that the bulge we say bulge a lot in this conversation here.
we have to.
But okay, so the bulge of the Earth, what it does is it creates a torque on the moon that slows the rotation of the moon down, and then over time, the moon slows down, and then eventually stops with respect to the Earth, and then that's why we only see one side of it.
And interestingly enough, right now, the moon is moving away from us at a rate of about 2 to 4 inches per year.
And actually, the reason for that is because once again, the good old bulge of the Earth is actually pulling on the moon, slowing down its orbit. The moon is actually moving slower and slower around the Earth every year by a small amount, but the reason why it's moving away from the Earth is because of the conservation of angular momentum, which has to do with which has to do with the velocity and like distance from the point of rotation and all that stuff. Mm-hmm. The actual equation is MVR, right? Mass, velocity, radius. If it's like a perfectly circular.
Yeah, I forgot the formula.
That's right. I'm pretty sure that's definitely so. Right. Mm-hmm. But so essentially, what I'm trying to say here is that the angular momentum is conserved, and so if the Earth is slowing down the moon, the velocity is decreasing. Then something has to compensate for that, and in this case, the mass is not changing, and so the radius from the moon to the Earth has to increase to compensate for that decrease in velocity.
How
and
is
so
the moon wait, isn't it?
Moves away.
Isn't it the other way around? Because the moon is actually pulling on the Earth now more than because the moon is already tidally locked with the Earth. Interestingly enough, and everyone's going to love this, Earth's rotation is actually slowing down. So one day is getting longer and longer every year. Now, obviously by a microscopic amount.
Wait, is that?
That's what I'm saying. I think you said it the opposite.
I think that's right.
I think you said it the opposite way. So basically the moon is actually tugging on the Earth. That's causing the Earth to slow in its rotation. Now, when the Earth is slowing in its rotation, the energy has to go somewhere. So that basically translates into the moon gaining energy and moving away from the Earth. And that's is simply because they are both not tidally locked to each other, but instead the moon is only tidally locked to the Earth and not the other way around. A common example, Pluto and Chiron, one of its satellites, are tidally locked to each other. So basically, if you look at this planetary system, they're always facing each other, which is like a really cool sight to see. And yeah, so that's basically why the moon is moving away, which is I think a really cool topic that you brought up that we got to talk about.
We actually did cover this entire topic.
Yeah, I think so. I think I recognize. I think a little bit of deja vu in this conversation for sure. Yeah, for sure. Well, I think we've spoken all we have to speak about. I don't think there's anything else.
If you guys have any questions, any
Yeah.
recommendations for episodes, make sure to send us an email, a comment, or a message on Instagram at math.physics.podcast. Go follow because we're almost at 1,000 followers.
Did I say that the 100K Q&A was up today in this
Yeah, you
episode?
did.
I don't think I
You
did.
did.
Did I?
Yeah, you
Oh, I
did, you
did.
did.
Okay, cool. Because I just wanted to mention it again. Go check out the
Yeah.
100K Q&A. It's on YouTube. It will be coming down from Instagram, right? So go check it out on YouTube.
Yeah.
Right?
Yeah.
Yeah.
Go check it out.
So it's
on
going to be
YouTube.
coming down on Instagram sometime this week. So go check it out on YouTube if you haven't already. For sure. Yep.
Other than that, I think that's it.
I think that is
Also, this is just a little PSA for my sake.
it. Okay.
If any of our listeners play chess, you can
Oh,
add me
nice.
on I play on leechess.com or .org, sorry. You can add me. I think it's just my name. I'll put it in the description. Anyways.
Nice.
Other than that,
That's
I
cool.
like to play chess, but so
That's awesome. That's awesome.
So I guess that's everything for today.
Yes, sir.
Let's just take a moment and
Let's
say
just
thank
take a
you to
moment.
everybody.
Let's just take
Thank
a
you to
moment.
everybody for listening to this episode of the podcast. This has been episode number 63 of the Math and Physics podcast, going for 1 year plus.
Oh,
Strong.
that 1 year.
1 year and 20 days, everybody. Congratulations.
Yep, May
to
9th.
us.
Yep.
All
Let's see
right.
it.
Yes, I am dragging this on. So I hope you enjoyed. I am your host, Parker.
And I'm Ray. And we will see you soon.
Bye, everybody.
Ayo, ayo, ayo.